Good day. Welcome to the second part of the discussion video on absolute convergence and tests for absolute convergence. Before watching this video, make sure na napanood niyo na yung first part ng ating discussion class. Katulad ng sinabi ko sa part 1, I have chosen these exercises from Math 22 module, page 58. So the instruction there is to determine whether the series is absolutely convergent, conditionally convergent, or divergent. So far, we are able to answer letter A. We are not able to finish the solution for letter B. For letter B, this is what we know so far. So we have let an be equal to this one for all n. We have shown in the first part of the lecture video, of the discussion video, that this infinite series is divergent. So from the first part of the discussion class, we have shown that this infinite series is divergent. In return, we have to check whether this infinite series is convergent or divergent. If this infinite series is convergent, since we know that this infinite series is already divergent, we can then say that this infinite series is conditionally convergent. But if it turned out that this infinite series is divergent, then for our conclusion, we say that this infinite series is divergent. As you can see, this is an alternating series since we have here negative 1 raised to n, and sine of 1 over n is always positive since our n ranges from 1 to positive infinity. Last time, I asked you to apply alternating series test on this alternating series. So, tignan natin kung parehas ba tayo ng nakuha na solution. So, we have here the alternating series of negative 1 raised to n times c sub n. So, there are two things to verify. The first thing to verify is to check whether the sequence of c sub n is ultimately decreasing. That is the first thing to verify. The second thing to verify is that it's the limit of c sub n as n goes to positive infinity equal to 0. So the first thing is to verify whether the sequence of c sub n is ultimately decreasing, and the second thing to verify is whether the limit of c sub n as n goes to positive infinity is equal to 0. If it turned out that these two things are true, then we can then say that this infinite series converges. Okay, so let's do that. So first thing to do is to check whether this sequence is ultimately decreasing. So how do we do that? We first let f of x to be equal to sine of 1 over x for all x in this interval. Our interval here is 1 to positive infinity since our n ranges from 1 to positive infinity. After letting f to be sine of 1 over x, we then look for f prime. In here, f prime of x is equal to cosine of 1 over x times negative 1 over x squared. Since our x comes from the interval of 1 to positive infinity, 1 over x squared is positive, times a negative number, we have here negative. So this is negative when your x come from the interval 1 to positive infinity, your cosine of 1 over x is always positive. Again, if your x is greater than or equal to 1, then cosine of 1 over x is always positive. So positive times negative is negative. So you have here less than 0 for all x in this interval. Since f prime is less than 0 for all x in this interval, we say that this sequence is ultimately decreasing. So that is for the first part of the alternating series test. For the second part, we have to verify whether the limit of c sub n as n goes to positive infinity is equal to 0. C sub n here is sine of 1 over n, so this is just the limit of sine of 1 over n as n goes to positive infinity. As n goes to positive infinity, 1 over n goes to 0, so this is just sine of 0, which is 0. So we have shown that the limit of c sub n as n goes to positive infinity is 0. Thus, by the alternating series test, we say that this alternating series converges. Since we have shown that the, the infinite series of the absolute value of a sub n diverges, and we have shown that this infinite series converges, we say that this infinite series is conditionally convergent. And this is our conclusion for letter B. Parehas ba kayo ng nakuwang sagot? I hope so. Let's proceed to letter C. We have this infinite series. As you can see, each term in this infinite series is non-zero for all n. Oh, mali. When n is 0, what is the value of the term? When n is 0, n squared over 2 raised to n is n squared over 2 raised to n is just 0 squared over 2 raised to 0. So this is just 0. So when n is equal to 0, the value of the term is 0. So instead of starting with n equals 0, we can start with n equals 1 instead. Again, the value of n squared over 2 raised to n is 0 when you consider n equals 0. So instead of starting with n equals 0, we can start with n equals 1 instead. Now, if you look at this term, this is non-zero for all n starting from 1. Again, n squared over 2 raised to n is now non-zero for all n starting from 1. Since that is the case, we can apply the ratio test in this infinite series. Let a sub n be equal to this one for all n starting from 1. So we try to apply the ratio test in this infinite series since each term in this infinite series is non-zero. Applying the ratio test, we have to look for this limit. Again, if this limit turned out to be less than 1, then we say that this infinite series converges. If it turned out to be greater than 1 or is equal to positive infinity, then we say that this infinite series diverges. However, if this limit turned out to be equal to 1, then we say that the ratio test is inconclusive. Now, replacing values for a sub n plus 1 and a sub n, we have the following. So this is your a sub n plus 1, and this is the reciprocal of a sub n. Notice that 2 raised to n plus 1 is just 2 raised to n times 2. So you will cancel 2 raised to n in here and 2 raised to n in here. So you will be left with 1 in here and 2 in here. So you can factor out the absolute value of 1/2, which is 1/2. So you have 1/2 here, and we know that n ranges from 1 to positive infinity. So the absolute value of n plus 1 squared over n squared is itself. So you have the following. And then evaluating the limit of this one, we get 1, and 1/2 times 1 is 1/2. So you have here 1/2, which is less than 1. Since we have shown that this limit is less than 1, we say from the ratio test that this infinite series is absolutely convergent. And this is our conclusion for letter C. Since we have shown that this infinite series is absolutely convergent, since this infinite series is just equal to this infinite series, as a consequence, this infinite series is absolutely convergent. And that's it for letter C. Let's now answer letter D. We have this infinite series. If your n ranges from 0 to positive infinity, each term in here is non-zero, since factorials are never zero. Since that is the case, we can apply the ratio test. Let a sub n be equal to this one for all n. We can apply the ratio test in this infinite series since each term in this infinite series is non-zero. Applying the ratio test, we have to look for the limit of this one. Again, if this limit turned out to be greater than 1 or is equal to positive infinity, then this infinite series diverges. If this limit is less than 1, then we say that this infinite series converges. However, if this limit turned out to be equal to 1, then ratio test is inconclusive. Now, replacing values for a sub n plus 1 and a sub n, we get the following. So this is your a sub n plus 1, this is your reciprocal of a sub n. Now let's look at this one. Let's look at this term. Now you have here 2n plus 2 factorial. This is just equal to 2n plus 2 times 2n plus 1 times 2n factorial. Let's look at this one. This is just equal to n plus 1 times n factorial and naka-square. So this is just n plus 1 squared times n factorial squared. Thus, this limit is just equal to the following. So we replace this one over here with this one, and then we replace this one over here with this one. As you can see, you can cancel out n factorial squared in here, n factorial squared in here, 2n factorial in here, 2n factorial in here. And we will be left with 2n plus 2 times 2n plus 1 over n plus 1 squared. Note that n ranges from 0 to positive infinity. So 2n plus 2 times 2n plus 1 over n plus 1 squared is positive. Therefore, its absolute value is itself. So this will just be equal to this limit. And as you evaluate the limit of this one, you'll get 4. We know that 4 is greater than 1. Therefore, by the ratio test, we say that this infinite series diverges. Again, since 4 is greater than 1, so this limit is greater than 1, we say that this infinite series diverges. So this is your conclusion for letter D. For letter E, we have this infinite series. So as you can see, n here ranges from 1 to positive infinity. Since that is the case, each term in here is non-zero for all n. Since that is the case, we can try applying the ratio test. So as an activity, I want you to try applying the ratio test in this infinite series. So bago nyo panoorin yung third video ng ating discussion class, i-try nyo munang i-apply yung ratio test sa infinite series na ito. Bago nyo panoorin, sagutan nyo muna on your own. And tingnan natin kung parehas tayo ng magiging sagot. Okay? See you on our third video. Thank you for watching. Bye!